brief introduction. I will try to keep it as brief as possible, and then I will leave the stage to you, Dr. Bixby.
Okay.
All right, so hello everyone. Welcome to our distinguished seminar series. I'm really glad to see that we have 125 people online today joining us. So today I'm very much delighted to introduce our distinguished seminar speaker, Dr. Robert Bixby from Gurobi Optimization. Dr. Bixby has held academic positions at a variety of universities, for instance, University of Connecticut, Northwestern, and after that, Rice University. And currently, actually, he's an emeritus at Rice University, as well as a visiting professor of mathematics department at University of Erlangen-Nürnberg in Germany. And also, for those of us from Canada, he also has an honorary doctorate in mathematics from University of Waterloo. So in terms of his research area, I would say confidently that he's a true expert on computational aspects of linear and integer programming. He has a lot of high impact publications, a variety of very prestigious prizes. I'm not going to go through the long list, but moreover, I would like to say that as all of you, especially those who took my integer programming class know very well, he co-founded CPLEX Optimization as well as Gurobi Optimization. And his contributions to the field, I will say, to the field of optimization, and you will hear his story overall, I believe, to some extent today, have been a huge inspiration to many of our colleagues, including myself. So with a great pleasure, I welcome Dr. Bixby to our seminar series.
Okay, thank you. Thank you very much for that very nice introduction. I'm going to see if I can successfully share my screen. Okay. Can you see my screen?
Yes.
Okay, excellent.
If we can get the full screen.
Yep.
I'll confirm. Perfect.
There we go. Ready to start. So that's my title, Optimization, Past, Present, and Future. Optimization is, of course, a huge subject, but in business applications, there are really two kinds of optimization that dominate: linear programming and first and foremost mixed integer programming. It's those two technologies that will be the focus of my talk. So when I talk about optimization today, that's really what I mean: linear and mixed integer programming. Here's a quick outline. I'm going to start with some historical comments that take us up essentially through the end of the 1990s. And then I will start talking about linear programming and mixed integer programming separately and try to give you a sense of where we are in these two subjects computationally. The emphasis in the end will be really on mixed integer programming, because that's where the applications are. That's the technology that companies really use today. And finally, a couple slides on my view of what the future holds for optimization. So the history of linear programming for most of us really began in 1947 with the work of George Dantzig. By the way, his old papers from then, if you have time to go back and read some of them, they're just fantastic. He had remarkable insights into where this subject was going, a subject that depends on the use of computers, and they didn't have any computers back then. It's really remarkable. And one of his big differences between him and the economists of the day who were interested in linear programming as well was that he saw value in actually solving linear programs and using the answers to make decisions. And consistent with that, he proposed an algorithm for solving linear programs, the so-called Simplex Algorithm, which is today, in one version or another, still the single most used algorithm for solving linear programming problems. The first, according to Dantzig, the first linear program that was actually solved, one that was real in some sense, that was solved using his algorithm was solved by an economist, Latterman, in 1947. It was an instance of the so-called Stiegler diet problem with 9 constraints and seven variables. It took 120, I suppose I should say, person days using desktop calculators. So we've come a long way since then. The first computer implementation that I could find was at the National Bureau of Standards, now called NIST, in the United States back in 1951 on a SEAC computer. And after that implementation, a more systematic development of linear programming codes started. And that was moved along by a joint effort between George Dantzig and a man by the name of Bill Orchard Hayes, who was really, by many, is viewed as sort of the father of linear programming computation. And his work, and together with Dantzig, really determined what happened in the 1950s. Starting off at the beginning of the 1950s, the first computer codes, it would take maybe, believe it or not, about 8 hours to solve a problem on the size of this, the order of this problem solved by Latterman. Progressing through the 1950s, by the end of the 1950s, following a sequence of introductions of new machines by IBM, linear programming had gotten up to maybe 200, 250 constraints. So developments were moving along relatively slowly. About the beginning of the 1960s, LP began to be used commercially, actually, for the first time, used primarily by oil companies, which at that time were actually the primary supporters also of research in linear programming. Moving on through the 60s, there was steady but slow improvement up till about 1970, which is the point in time in which mixed integer programming in a pretty primitive form became commercially viable for the first time. And the computing environment that was available at that point, and that was really influenced a lot of what happened, was the introduction of the IBM 360 computers. And along with that, there were two very influential codes that were developed, MPSX 370 in the US, and Umpire, which was developed in the UK, primarily under the direction of Martin Beal, who was also one of the pioneers in this subject. Those two codes were written for mainframe computing, and they were written in machine language to run on those specific computers. Moving into the decade of the 70s, interest in optimization flowered. There was just numerous new applications that got identified. Large-scale planning applications were particularly popular. But at the same time, significant difficulties emerged. Building applications was very time-consuming and very risky. Development cycles were like, it's crazy, but it took 3 to 4 years to build an application. And the applications were complicated to use. Really only the people who developed them could use them. If that person was no longer working on the application, you couldn't use it anymore. Not only that, the technology just was not ready. Linear programs were still very hard to solve, and mixed integer programming, which we'll be talking about extensively later, was a complete disaster. And one of the results of that coming out of the 70s was a real disillusionment. First and foremost with mixed integer programming, that it was kind of this toy and fun to talk about, but totally hopeless to solve. Moving into the decade of the 80s, by the mid 1980s, which is, by the way, roughly the time that I got involved in these subjects, there was a perception that linear programming software had really progressed about as far as it could go. MPSX 370 and its follow-on MPS 3 really dominated. People had tried to improve on them for years and had been totally unsuccessful. But the fact that the subject had stagnated and people felt there was nothing more to do didn't mean that these were solved subjects. Linear programming was far from a solved subject. And then there were several key developments in this decade, one of which was the introduction of the IBM PC. It wasn't the first mini computer or desktop computer that got introduced, but it was the one that really brought desktop computing to business. Relational databases were developed, separation of logical and physical allocation of data, and that was really the genesis of ERP systems that are so commonplace today, and it's really the genesis of the massive amounts of data that we now see available to businesses. And there was also this incredibly important paper by Karmakar in 1984, in which a practical interior point polynomial time-bounded algorithm for linear programming was introduced. And that event just reinvigorated the whole subject of linear programming. I think within a year or two's period after the publication of his paper, there were something like 2,000 papers that were written related to Karmakar's work. So I'm going to take a little pause here from the general history and just talk about my own history briefly. I got my PhD in 1972. I worked on very theoretical, really pure math version of operations research, something called matroid theory, up till about 1985. In 1983, I began for the first time to do computer programming. I knew nothing about computer programming at that point. I knew nothing about numerical analysis, I knew nothing about the practice of linear programming, but I started writing some codes for my classes. And then for a reason that still to me this day is, I don't understand, really a friend of mine, Tom Baker, who worked for Exxon Corporation, he started one of the first supply chain optimization companies called Chesapeake Decision Sciences in that time. And he actually contacted me and asked me if I could provide him with a linear programming code to use in his software. I thought he was crazy. I mean, why is he asking me to do this? But it seemed like an interesting challenge. And so I converted something I was using in my classroom to a form that he could use. And he started using it. And this kind of became a hobby for me for a couple of years. It wasn't my research. I didn't look at the literature. I didn't pay attention to what anybody was doing. And I just kept beating away on this code with using the models that Tom Baker would send to me. And then much to my surprise, much to my amazement, I thought this code was actually terrible. I got a request in 1987 through Tom Baker from Amico Corporation to actually buy a license to my code. I couldn't believe it. And this led me for the first time to actually compare what I developed to one of the standard codes that people were using at that time, a code developed by Roy Marston called XMP. And much to my amazement, what I thought was a terrible code was actually 4 times faster than this code that was in common use. And at that point I decided, well, maybe I could make this into a research topic. All of my friends told me I was absolutely crazy. This was nuts. Linear programming was done. I was wasting my time. And I have to admit, I had zero success initially in getting research funding for this. So the upshot of that is couldn't get research funding for it. So I started a company, which was co-founded with Janet Lowe, and that was CPLEX Optimization back in 1988. And that's really the point in time in which I got serious about computation and linear programming. So back to the general history, the decade of the 90s. During this period, it was an incredibly exciting period if you were working in linear programming. Performance literally exploded, literally took off. Primal dual log barrier algorithms completely reset the bar for computation, and quite unexpectedly, simplex algorithms kept pace. During this period, data became plentiful and accessible for the first time. ERP systems became commonplace, SAP's R3. And popular new applications began to show that integer programming could work on difficult real-world problems. So you couldn't just solve out-of-the-box general-purpose mixed integer programs, but people demonstrated that if some problems in the airline industry and some supply chain problems, if you focus on a particular problem, built some special purpose algorithms and cutting planes and whatever all that stuff was, you could actually solve some problems of practical interest. So that brought us through the 1990s. And the question is now, where are we today with linear programming and this funny subject that I haven't really defined yet called mixed integer programming? I'm going to start with linear programming. The presentation is going to be briefer than I would like because I really want to save a little bit more time to talk about mixed integer programming. I'm going to start with just one example that illustrates the kind of, for me, very exciting things that were happening in the 1990s with linear programming. And then I'll show you some results that kind of summarize the enormous computational progress that we made in those early years with linear programming. So here's my example. This example is a model that it was given the name at the time, LAU2. LAU is United Airlines spelled backwards, if you will. That model was actually a fleet assignment model, an early example of fleet assignment model, which is a model that takes a particular time period for a particular airline and assigns airplane types to flight legs. Those kinds of models were notorious for being difficult for linear programming. And United Airlines put a challenge model out there that had, by today's standards, wasn't very big, 4,000 constraints and about 6,000 variables. And the challenge presented by United Airlines, as described to me by John Gregory at Cray Research at the time, was that if you could solve this, that means if a computer vendor could solve it, United Airlines was willing to spend a bunch of money on those computers. I was working together with John Gregory and Cray Research on a version of CPLEX to run on the Cray computers at that time. Those were the supercomputers of the day. And so John asked me to get involved. And the following is a brief version of the story of what happened. So going back to 1987, the first attempt I made to solve this model, I made on a Cray XMP, which was the fastest machine on the planet at that point in time. And my wonderful CPLEX code from back then failed miserably. It actually got stuck in what we call phase one. It couldn't even find a feasible solution. It was just getting nowhere. And when I looked at it, I realized it was having enormous problems with what we call degeneracy. Degeneracy is something you always hear about if you study linear programming in school. But the general feeling at that point in time from the practical side was that, you know, theoretically it was an issue, but in practice it wasn't an issue. You didn't need to worry about it. Well, that just turned out to be wrong. So the first thing I had to do was introduce something in CPLEX to deal with degeneracy. So I invented a new method, not something that was in the textbooks, and implemented that. It was pretty straightforward. And so then the problem was solvable, but it was still incredibly slow. Shortly thereafter, John Gregory got in touch with me and reported that it turns out that this code, OB1, OB1 was the research code for interior point algorithms. So the research code for the ideas of Karmakar in those days. And it was developed by Irv Lustig, Roy Marston, and Dave Shano. OB1 was able to solve it on a Cray XMP in 1200 seconds. And John Gregory's advice to me was, forget it, it's hopeless. The simplex method will never solve this problem that fast. Well, I ignored what he said and thought about it a little more. And I got this idea, simple idea, you know, this problem's really degenerate, but maybe this transpose of the problem, the so-called dual formulation, isn't quite so degenerate. So I quickly implemented a piece of code and transformed the problem into its dual and solved it with the standard primal simplex algorithm. And bingo, it was much faster. So we were close, still not as fast as 1200 seconds, but closer. And I was aware at that time that there was something actually called the dual simplex algorithm, introduced by a game theorist by the name of Karl Lemke back in 1954, as I recall. And it really hadn't been taken seriously and implemented seriously for practical problems, but it seemed like a natural choice in this case. So I quickly built an implementation sort of based on some standard ideas. And that got closer still not up to the 1200 seconds, but we were closing in. And then another idea came along, and this actually came from a guy by the name of John Forrest, he's still somewhat active in the field, actually a very smart guy who was behind, a Brit, by the way, who was behind a lot of the developments at IBM, at the IBM codes in this period of time. And he managed to show that primal simplex algorithm, together with something called DevX, could have some success on this model. Now, DevX was an idea, it's Latin for steepest edge, so it was an approximate steepest edge algorithm. It was proposed actually by a very smart woman who worked for British Petroleum in 1972 by the name of Paula Harris. And he was having some success with that. And I thought about it and said, well, if he's having success with something related to steepest edge in the primal, it ought to work even better in the dual. So I actually looked up the mathematics and did some derivations and implemented a dual simplex algorithm with steepest edge. And what do you know? That was now the fastest algorithm. It was faster than the interior point algorithm. And I was excited. This was really fun. I immediately, after that, got in touch with Don Goldfarb. You may not know that name, but Don Goldfarb is a pretty well-known guy in the optimization community. And he is really the guru for steepest edge. That's how I knew him in those days. And I thought he would just be excited to know that his ideas were being so successful in practice. So I got in touch with him and told him what had happened. He was totally unimpressed. He said, his first question was, well, what steepest edge algorithm did you implement? And I described it to him. He said, no, that's not the right one. There's a much better one. And he described it to me. Essentially, it involved projecting out the slack variables in the dual problem. So I quickly implemented that algorithm. And it was not only faster, it was faster by a bunch. It became And what happened as a result of all this? Sort of what's the punchline at the end? This development, that particular idea, dual simplex algorithm with steepest edge, is to this day the basic algorithm that is most commonly used to solve linear programming problems. It's a fascinating development. So that's one model. Where are we today in general? In 2002, I did an extensive study of the improvements in linear programming for the period that I had been involved in it. Of course, this is not just my work, but it was during the period that I was working on the subject, 1988, and I updated those results a little bit later in 2004. And I broke the results into two parts, the developments, the improvements that came from the algorithms, the mathematics, and the improvements that came from the machines. And of course, we know in that period of time, machines got a lot faster. So the algorithmic part, and I did a pretty careful study, it was published. I compared primal simplex algorithm in 1988 to the best of primal, dual, and barrier in 2004. Now, you might say, okay, that's cheating. You're comparing one algorithm to three algorithms, but we only had one algorithm in 1988. We didn't have three. And in any case, that's the way I did the comparison. You can accept it or not. I got a factor of improvement of 3,300 just due to the algorithms and the computer science and the mathematics. The improvement of machines in that time, as I measured it, 1,600, only half as much. You won't find very many places where the algorithmic improvements and the mathematics contributed more than the machines, the computation. And of course, these are independent, so you can multiply them together. This gave a remarkable 5 million-fold improvement, which transforms, if you want to think about it, 2 months into something like a second. So in that period of time, linear programming had literally been transformed. Just a quick comment on what has happened since 2004. It's interesting that there was a new period of stagnation between 2004 and roughly 2015, in which really nothing happened on the algorithmic side for linear programming. That has changed, fortunately, in the last 5 years or so. On larger models now, LP algorithms in general have improved independent of machines by about a factor of 3x. And some of the key ideas have been something called soft symmetry. And actually, I may come back to this a little bit later, machine learning has played a role. Tonghao Gu has actually a nice presentation he gave recently on some of these improvements. And anybody who's interested, I can point you to that presentation. So in summary, where are we today in linear programming? If you ask practitioners about it, they will tell you linear programming is for them a solved problem. Large models can now be solved robustly and quickly. They regularly solve models with millions of variables and constraints. So linear programming has now become this incredibly powerful tool in optimization that's available to us. And that tool, its main application is that it helps us solve mixed integer programming problems. So that's my next topic, mixed integer programming. And let me give you a definition so that we're on the same page as we move forward of what is a mixed integer programming. So those of you who know anything about the subject will recognize, so it's a mixed integer programming is optimization problem of the form given at the bottom. And the first 3 lines of that definition, that defines a linear programming problem. So really, a mixed integer programming problem is a linear programming problem together with the added conditions that some or all of the variables have to take on integer values. Now, you might ask, I said, what are you introducing a definition like this for? This is crazy. What you're doing is you're taking linear programming, which is well solved. There exists a polynomial time algorithm for it. It's robust. And you've added these conditions that make the problem non-convex, that you make it NP hard. All of a sudden, you've got this problem. At its core, we fundamentally have no idea how to solve. Why would you do that? And the reason is adding this ability to have integer variables enormously grows the applications of this, because you can now model decisions. You can have a variable, this is 0, 1 variable, Those are the only allowed values. 0 corresponds to, say, not building a warehouse. 1 corresponds to building it. 1/2, 1/3, 3/4 doesn't make any sense. That ability to build in decisions has transforms this into a subject that has enormously wide applicability. And I've just got one slide that attempts to give you a picture of that before I move on. And I apologize, this is a bit of a marketing slide. My purpose here is not to market, is not at all to market Gurobi, but just to give you a sense of, on the practical side, where we are today. Gurobi has more than 2,500 customers worldwide, globally, all over the world. Application areas, I often get asked about, well, what are the application areas for this technology? It's essentially limitless. These are, by our count, these applications cover 40 plus different industries. And you can see over with those logos over there, some of the biggest corporations in the world. In fact, last time I checked, 8 of the 10 biggest companies by net value of those companies on stock exchange are using mixed integer programming in some important way in their business. It has become an indispensable tool in the management of the modern enterprise. So what got us there? What got us there is this ability to model and our ability to solve these problems. So let's talk about that now. How do we solve mixed integer programs? The basic algorithm is actually brain dead simple. It's something that we call, we give the name linear programming based branch and bound. It's a divide and conquer algorithm. Here's how it works. You take your mixed integer programming problem and you don't know how to solve it. But so what do? You throw away the integer restriction. What's left is a linear program. I know how to solve that linear programming. I have robust algorithms for that. I solve it. I stare at the answer. Now, if I get lucky and every variable that was supposed to be integer by chance turns out to be integer, you win. You've solved the mixed integer programming problem. Of course, that rarely happens in practice. So what do? You stare at the solution, look around, find yourself a variable by some sort of choice method. Say in this case, I find a variable called v, and it has a fractional value of 3.5 in the optimal solution. We'll just add 2 constraints that forbid that value. I will round it down to less than or equal to 3 and round it up to greater than or equal to 4. That breaks my original problem into 2 problems. And it's pretty clear, is it not, that if I can solve each of those 2 problems, I can put the answer together to solve my original problem. And we just essentially repeat that procedure. And as we repeat it, we keep track of 2 very important pieces of data. So when we get deep enough into the search tree, eventually you've done enough of this rounding up and down that you force the solution into a corner, and you do in fact get an integer solution. As soon as you get that, you have an actual feasible solution to your original problem, and you've got a value, an objective value corresponding to it. That value, assuming you're minimizing, I always assume that I'm minimizing. If I'm minimizing, I know I never have to accept from that point on anything worse, anything that's higher. That gives me an upper bound. Slightly less obvious, if you look at any point in time, all of the active leaves in the search tree, and you look at the linear programming relaxation values for each of those, take the minimum of those numbers, that gives you a lower bound. The difference between that upper and lower bound at any point in time is called the gap. And the essential overall idea with this algorithm is to drive the gap to 0. When you do that, you have a proof that the best solution you have in hand is the optimal solution. Of course, in practice, users typically don't wait for a proof of optimality. They'll stop when they're within 5 or 10% of optimality. That's more than enough. And one more point I want to make before we leave this slide. Some people look at this and they say, "Oh, come on. This isn't going to work. You're just enumerating. This is just divide and conquer." You're going to end up, problems like this have billions and billions of integer solutions. That's all you're doing is enumerating. It's not true, because at each of these nodes, you are taking a version of the model, which is an LP relaxation, and that approximation to the model, you are solving globally. And that's what saves our bacon in the end, our ability to solve linear programs, together with a lot of other ideas in the end. So I'd like now to just show you a couple of examples before I move on to give you some computational results for mixed integer programming. And part of the motivation for this is we're talking about mixed integer programming here. And I've pointed out already that it's non-convex, it's NP hard. It really is NP hard. I would hate, in spite of what I'm going to claim is an enormous growth in our ability to actually solve real world mixed integer programming problems, I don't want you to come away from this talk with the impression that we can just solve arbitrary mixed integer programming problems with a robust, dependable algorithm with a performance guarantee, a reasonable performance guarantee. It's just not true. It is NP hard. And here's an example that illustrates that. This is a small but difficult model, and it's a real model, by the way, somewhat real. It was developed actually by a customer of CPLEX many, many years ago. I think it was a French bank, actually. That's a model with 44 constraints and 51 variables, a maximization problem, not minimization. It has all of the variables in this problem are what are called general integer variables. So not just 0 or 1, could be any integer value. And there are no bounds on the variables. Now, anybody who works in this subject, practically speaking, will look at that and say, you're nuts. What real problem has no bounds on the variables, for God's sakes? You can't produce an infinite amount or back order an infinite amount, but that was the model. And here's what happened in the initial attempts to solve this model. I ran the version of CPLEX that was available at that point in time, a number of years ago. And immediately you get an integer feasible solution with a value of, turned out to be minus 2,186. This is a maximization problem. So that gives you a lower bound, not an upper bound. And from the linear programming relaxations, you get an upper bound. You instantly get those two numbers that I put there. And then I ran it for like a day and a half. It generated 32 million branch and bound nodes, a search tree that took up 5.5 gigabytes of memory, all of which is wonderful if you're a software engineer, looked pretty cool flying by on the screen. The unfortunate thing, nothing had happened. The two bounds had not moved any closer to each other. And in fact, to my knowledge, to this day, this model has never been solved. What's wrong? Now, I would claim what's wrong here is bad modeling. The free general integer variables in this thing, the general integer variable without bounds, they literally chase, it's like a dog chasing its tail. They chase themselves off to infinity. And here's the most mathematics you're going to see in this talk today, by the way. A gentleman by the name of Ed Klotz, who for many years was part of the CPLEX development team, is now part of the Gurobi development team. Very clever guy. Looked at this model and extracted from it the essence of what's wrong, at least in my view. He built this little 3-variable instance that you see before you. Maximize x plus y plus z. I mean, it's a silly, simple little problem, right? 2 constraints, one of which is a stupid constraint, says set z equal to 0. All right. The variables, the 2 variables x and y, are free integer variables. I can take on, as in the example, any value. Now, you don't need a fancy code to solve this. If I give you 10 minutes to go away by hand, you'll figure out that an optimal solution is x equal y equals z equals 0. All right. But let's just think systematically for a second about how we might solve it. So one way might be the following. Take that z equals 0 constraint, substitute it out. That leaves you in the objective function with maximize x plus y. X and y are integers, right? So you know the objective function has to be integer value. Taking that into account, solve the linear programming problem, you will instantly conclude that x equal y equals 0 is optimal. Here's another one, which I actually like a little bit better, based on something called the Euclidean reduction. Look at that constraint, 2x plus 2y less than or equal to 1. 2 evenly divides the left-hand side. So divide the constraint by 2. You get x plus y less than or equal to a half. Well, if x and y are integer and the sum is less than or equal to a half, it's sure as suit got to be less than or equal to 0. So you can replace a half by 0. If you do that, solve the LP relaxation, you win, you're done. The interesting thing about this problem is if you turn off these logical kinds of reductions, which are what we call pre-solve, an analysis that goes on before the application of LP-based branch and bound, CPLEX, Gurobi can't solve the model. They'll run forever. All right. So again, mixed integer programming is NP hard. Don't forget that. Well, my next and last example is one that I think is more typical of what we say of C for real mixed integer programming problems. This is a problem from the, or a class of problems really from the electrical power space, which is one of the more popular areas these days in which mixed integer programming gets applied. And the particular instance I'm going to talk about is something called a unit commitment model. It's a model that appears and is used in the industry in a variety of different forms. Probably the simplest one to describe is what's often called the next day model. In the next day model, what you're doing is you're looking at a particular transmission network of power generation plants, and you're deciding on the day before which entities will be used to generate power on the subsequent day. That's called a unit commitment problem. People have known for years that these these models could be modeled as mixed integer programming problems. Well, in that regard, here's a quote for you from an industry publication back in 1989. Mixed integer programming is a powerful modeling tool. They are, however, theoretically complicated and computationally cumbersome. In other words, mixed integer programming, interesting, it's a fine toy, but forget about it. It just doesn't work in practice. That was the attitude those many years ago. Well, I'd like to jump forward from there to 1999. It was a meeting that was organized at Rutgers University at the DIMAX Center at Rutgers University in 1999. It was organized by a guy by the name of Dick O'Neill, who worked and still does actually work for the Federal Energy Regulatory Commission in the US, FERC it's called. He is an industry expert. He knows these models and how they're used inside and out and backward, but he also has over the years kept touch of what's going on in the research community, in particular what had been going on in mixed integer programming. And he was aware in 1999 that some stuff had been going on in the research community. It would probably be good to connect up the practitioners with these researchers to see if there was some benefit to be had. So he invited a bunch of industry people to this meeting, and he invited a few MIP experts. I was one of those. The very first talk of the whole meeting was given by one of the practitioners, and the subject of his talk was a model that's still available today, actually, as in the public domain, labeled Unit Cal 7. It was an instance of the California 7-day unit commitment model. Not a trivial model by any means, at almost 50,000 constraints and 26,000 variables, of which about 3,000 of which were binary variables, making it a mixed integer programming problem. The speaker in the session began as follows. He did what people often do in practice. He looked at this problem. It was big, it was extremely difficult. And instead of trying to solve it directly, he reduced it to the 2-day model and saw what kind of results he could get from that. Let it run for 8 hours on a mainframe with one of the standard codes available then. Probably, I don't know for sure, but it was probably this MPSX 370 code that I previously mentioned, I think a couple of times. After 8 hours, it had made no progress toward optimization. The mixed integer program was obviously hopeless. So what he did is, again, what practitioners often do, he went to the 7-day model that he was really interested in talking about, and he solved the LP relaxation. That took an hour. And he looked at it and rounded variables up and down and talked about the implications of that and whether the solution was useful. That was his talk. Well, after this talk was over, of course, I knew that some interesting stuff had happened in the subject, and I literally chased this guy around the room. It can't have been a pleasant day for him. He finally acquiesced and gave me access to the model at the end of the day, and called up some coworker, and they put together a file and made it available, and I logged in somewhere and downloaded it and ran CPLEX on it. And here's the result. I ran the full 7-day mixed integer program, not just the linear program. And amazingly, CPLEX 6.5, which was the new version of CPLEX at that point in time, solved the whole model to optimality in 22 minutes. So I was completely blown away, and I immediately asked for permission to give a talk the next morning in the meeting. And so they gave me a half-an-hour slot, and I talked about these results, and they were blown away. I've talked to people since who were at this meeting. Actually, I was at one of these FERC meetings about 5 years ago, and they were at this thing, and they said that's literally the point in time at which they realized, wait a minute, we can really use mixed integer programming. And by the way, today, I don't know, back in 2017, you could solve this problem in 17 seconds. Today, it's probably 2 or 3 seconds. I haven't checked recently. Probably solve it on your cell phone in a few seconds. So with that example in hand, where are we today? So, well, I'm sorry, I got a little bit ahead of myself, excuse me, and I've got to be careful. I guess I've got about 10 minutes left. Is that about right? Yeah, I'll have to go fast, sorry. So where did this come from, this improvement? Well, I like to explain it with a little bit of a computational history in mixed integer programming. And that history, and I'm going to abbreviate it now, started in 1954 with a beautiful paper by Dantzig, Fulkerson, and Johnson, in which that's the same old George Dantzig. They solved a 42-city traveling salesman problem to exact provable optimization. It's an amazing paper. It's still worth reading today. Jumping forward to about 1974, 76, as you see at the bottom on the left-hand side, some pretty powerful codes had been developed at that point. MPSX 370 and Psychonic, which was this code a version of this code that got developed in the UK. Very, very good codes. They had good linear programming codes in them and some common sense branch and bound rules for solving mixed integer programs. But then something interesting happened. There ensued a period of almost 20 years in which there were enormously important developments on the side of combinatorial optimization, developments in cutting planes. And people actually proved, there were papers that showed that these things were all computationally useful, but in the end, none of the commercial codes were using these ideas. And we recognized that, and literally, Songhao Gu and Ed Rothberg sat down and rewrote the CPLEX mixed integer programming code in 1998. And this led to enormous changes in the underlying code. I don't have time to discuss them in any detail, but by far the two most important were pre-solve. We talked about pre-solve a little bit already, and cutting planes, particularly Gomery mixed integer cuts, which had long been dismissed as only of theoretical interest, and so-called mixed integer rounding cuts, which are closely related to Gomery cuts, as it turns out. So where did that bring us today in terms of how much faster we can solve mixed integer programming problems? So over the years, I've done a bunch of computational testing, and I'm going to summarize all of that testing in one graph that I'm going to show you in a couple of slides. There are two parts to that testing. First, the CPLEX part from 1991, the first CPLEX version that had mixed integer programming, up to about 2008. That's when Gu, Ed, and I left CPLEX and formed a new company. I didn't have access to CPLEX after that, so the testing after that was with Gurobi. These tests were all done with practical mixed integer programs that we had collected from customers over the years. In the case of CPLEX, that was 1,852 models. In the case of Gurobi, it's now grown to something like 6,300 models. And I ran with defaults and compared version over version moving through the years. And by the way, here's a picture, you will, of sort of a scatter diagram of the number of rows and columns of some of the models that appear in the Gurobi library. And what you can see is that the models have gotten very big. We have models with some with as many as 100 million variables in them from customers. And we regularly get problems with 1 million variables or 1 million constraints. And you can see also there's a rich variety of sizes of models and so forth. So this is a really good picture of what real world models look like. So here's the summary of my testing. Now, this is a lot to swallow all at once, but I'll do my best to explain it quickly. I want to focus on the version over version speedups, what you see as a label on the y-axis at the left. And I want to describe to you what these bars on this chart mean. So we're doing version over version comparisons. First, version 1.2 is compared to 2.1 of CPLEX, then 2.1 to version 3, et cetera. So what does this bar above the 1.2 to 2.1 mean? What we did is we took those 1,852 models, that's how many it was, ran them with defaults for 30,000 seconds with each of the two solvers. I got a list of over 3,600 numbers. I formed 1,852 ratios where I divided the solve time by the presumably faster code, which was 2.1, into the solve time for the old code, which was 1.2. I get 1,852 ratios. And I take the geometric mean of those ratios. You never want to take the arithmetic mean. That's really misleading. You take that geometric mean, it turns out what you get is the height of that bar, about 3.1. So that's a scientifically accepted way to compare versions of things these days. And it says that version 2.1 was about 3.1 times faster than version 1.2. And you see these developments through the years, and you see two particular bars that are higher than all the rest. There's one in version corresponding to version 3, and that really corresponded to the maturity of this dual simplex algorithm that I talked about a little bit earlier. That's fundamental to mixed integer programming. And then you see this bar that's much bigger than all the rest in 1998 with the introduction of version 6.5, which I've already mentioned in connection with these unit commitment models. There was literally, amazingly, a measurable close to 10x improvement in one version over another. And it came from this mining of the theoretical backlog. If you go back and you talk to people, integer programming researchers who were around at that time and aware of these developments, if you asked them, I asked Martin Grutschel actually before this, did he think it would ever be possible to have a general purpose mixed integer programming code that you could use to solve real world problems out of the box? He would have said, nah, not possible. And after the development of 6.5, that's what changed. It now became thinkable, possible, that you could take a solver out of the box and you didn't have to modify it. You can use it as a user to solve your problems. And that really changed the subject. So look at all those improvements over the years. You see this dotted line in the middle. So that's a topic for discussion. It's based on the claim that the first version of Gurobi that was released was roughly as fast as version 11 of CPLEX. That's arguable. I think Toby would argue with that. That might be off by a factor of 1 or 2, but that doesn't change the basic conclusion here. Let's just assume that they were roughly the same. You get this graph, and you multiply the improvements version over version. This is all machine independent up through version 9.1. You get this amazing factor of close to 4 million. And that's independent of machines, doesn't even take the machine improvements. Mixed integer programming today is, even compared to what it was 5 years ago, has just progressed enormously. It is really this incredibly powerful tool that can now be applied and is applied regularly to solve real problems. So I want to make some comments about the future. They will be abbreviated, but they're important to me. So in my view, you won't be surprised, optimization has a very bright future. Central to that future is the confluence of 3 events: the explosion of the availability of business data, which we're all aware of, new broad corporate focus on extracting value from that data. So even at the CEO level these days, and this was definitely not true 5, 10 years ago, there's a recognition that you need to use analytical techniques somehow to exploit your data. And together with that is the ever expanding power that we've just looked at of optimization to extract value from that data. So accompanying all of the events, of course, and many of you will be aware of this, there's been an explosion in the application of so-called AI techniques. All right? Companies are regularly using machine learning, AI, data science. These things go under various names, but they're in massive use. So how does optimization fit into this picture? Well, optimization, at least to some point, was largely overlooked for a variety of reasons, unfortunately. One reason was this perception that it didn't work. That's fueled by these developments that there's still remnants of that around from the 70s. Plus, there's so many computer scientists who work in these subjects, and they're taught that NP hard means you can't solve it. And so they just believe, unless they actually look at the data, they just believe out of the box you can't solve mixed integer programs. They're wrong, but they don't know it necessarily. And the second thing is the high skill level that this stuff requires. You can't solve a mixed integer program unless you first build a mathematical model. And that for many people has been a hurdle. So what has changed? Well, as we've seen, solver capability has undergone an absolute revolution. Second point, a little more subtle point, the widespread use of machine learning has actually legitimized the role of mathematics in AI and in applications. I don't know if you realize it, but machine learning, it's used a bunch, but like we estimate roughly 80% of the machine learning applications that are attempted fail. And people have learned that you really need to understand the mathematics behind what you're doing. They're accepting that you have to have that level of understanding to use these techniques. And as a benefit of that, we no longer have to apologize for the fact that you have to build a mathematical model to solve an optimization problem. So we're in the game for that reason. And then in addition, the increased robustness of the solvers, not just the fact that they're faster, and the enormous improvements in the software environments, nothing particularly to do with optimization, just in general, have made it possible to embed these applications in business applications, deploy them, and to users with a widely variety of skill levels. And the result is that optimization is indeed becoming widespread, and it's definitely viewed by most people now as a part of this AI revolution that we're experiencing. I think that's it. Thank you very much. Sorry, I'm a minute or two late.
Thank you so very much. So it's been a fantastic talk. I truly enjoyed it. Thank you so very much. So for those of you who might have to leave, please feel free to leave the meeting. But for those who are interested asking questions, please feel free to post your questions in the chat screen in the Q&A part, I believe, and we will help to ask them to Dr. Bixby. And by the way, for graduate students and the postdocs, we will hold a meet and greet type of a discussion session with Dr. Bixby following the seminar shortly. So maybe we'll take a 5-10 minutes break and then join that session and have a more informal chat, if you like. So you can also bring your questions to that session if you like. So
that's a separate session I need to
yes.
Join? Okay.
Yes.
So I should say goodbye to this session and go join that one.
So maybe let's wait for a few minutes in case anyone would like to ask questions about the talk here, and then we can maybe take a brief moment and then join the other one whenever you like.
Come on, there's got to be a question.
Currently in the Q&A panel too, actually.
Oh, sorry, it's my bad. I'm missing.
No worries.
So, but Laura, can we maybe let these people to ask in person? That'll be better. If we can
they can as well if they'd like. So if anybody wants to raise their hand.
Elias, would you like to go ahead first?
I have to enable their microphone. 1 second.
Okay, yes, you hear me?
Yes.
Yeah, not only that, I can see a picture of you.
Okay, cool. Thank you very much, Dr. Bixby, for this great talk. I personally, since I got into this field, I wait for this type of talk at Informs or something to kind of get a sense of the state of the field. So my question is about more complex integer programs. So mostly you were talking about, deterministic kind of single stage, single objective MIPS,
Yes.
where there's a clear massive improvement over the years. Can you say anything about more complex MIPS, say, stochastic, multi-stage, multi-objective, things like that?
So, yeah, that's a good question, of course. Let me see what's the best way I can think to answer it. So let's go to stochastic optimization. That's actually, it's interesting that Dantzig, back as early as the late 1940s, early 1950s, pivoted relatively quickly from linear programming to stochastic optimization as the problem that people really cared about, or should really care about. So this is, by the way, if nothing else, just evidence again of the remarkable insights that he had. The fact of the matter is that in spite of the fact that this happened so early, it really, even to this day, there have not been a lot of success in producing software like general mixed integer programming software that you can use sort of out of the box, or frameworks that you can use out of the box for stochastic optimization. There have been various attempts. IBM put something on the market, and it actually got used by a few people internally, but was never used substantially. I think Frontline Systems has built a system that works in the context of Excel, that sort of combines the data collection part with an approach. And I think they've had some success with that. Robust optimization, which a number of you will know about, is a pretty nice, interesting subject. Unfortunately, in practice, the kinds of bounds that you end up putting on things in robust optimization have been too conservative for people to use these things in practice. Now, I will have to say, I'm not as up to date as I would like to be. I have the sense that there has been some significant progress in the last couple of years. I mean, there has been one subject sort of moving away from just pure stochastic. Mixed integer nonlinear programming has definitely been of interest for some time. Users have been telling us they want to solve these problems for years. That won't surprise you at all, I'm sure. But it has been fairly recently an improvement. There's a new, I don't want to be tooting Gurobi's horn specifically here, but we do have a new bilinear solver that is actually quite nice and has significantly reset the bar for what's possible with these kinds of solvers. And for the mixed integer nonlinear programs where the nonlinear part, the non-convex part, can be treated with the bilinear solver, that this represents a real move forward. So there's been some progress there. That's my answer, best I can do.
Yeah, this could be a whole another hour of discussion, I bet.
Well, sure. I think actually you can almost say more about it than I can, right?
Yeah. So we have a couple more questions, if you don't mind. Ian, would you like to ask in person? I guess, Laura, you need to allow the microphone.
Sure. Hi, Dr. Bixby. That was a great talk. I just had a quick question about when we're comparing performance of these algorithms, and we're sticking with, a small, not a small set, but so a set of benchmark instances. How do you make sure that you're not overfitting to those instances?
Oh man, that's a super good question. We actually have a testing paradigm that we use internally that receives a lot of attention, and that is to say, we think about it a lot and we modify it over the years. So when we do tests internally, first of all, we're constantly updating the test bed. Now, there's certain biases built into it because it is based on the models that we have access to. Just probably biased a little bit to difficult models. Those tend to be the ones people send to us. There's probably a little bit of bias there. I don't know that that's so bad. And also there's a bias in terms of solvability. So if the models are not solvable, we don't, within some reasonable time, we really don't have a reasonable way to test them at this point. Probably some more thought should go into that. So with those two caveats, what we do is we build a model set. That model set is regularly updated, and in the end, we run it with 5 different random seeds, and we change those random seeds over time. And this is a really attempt, and there's a lot of in these codes, there are a lot of places where you make decisions inside the code where you have to break ties. And mixed integer programming has the property that you make one little change in one place it can easily send the search off in a completely different direction. So, you know, changing these random seeds can actually have a pretty significant impact. And we then look at the, you know, average performance gains using geometric means over these 5 seeds. And we have to get and we're very careful. We test the machines regularly to make sure that they're comparable machines. And we're very, very careful about making sure nobody else is on them. We can actually determine that we can measure improvements on the order of, believe it or not, 0.2% reliably. Now, whether this completely deals with the issue of getting into some sort of local minimum, but overtuning, you can still argue about that, but we certainly think about it and do our best to try to avoid it.
Awesome. Thanks a lot.
Thank you. So we have a couple more questions. Maybe we can try to briefly answer as well. So Cheng is the next one who would like to ask a question.
Hi. Thanks, Dr. Bixby, for the talk. I learned a lot from it, and I really enjoyed it. And my question is that, like you mentioned that there are this algorithm that you find in the literature that's very good and no one implemented it, and like some people from Gurobi or Simplex implemented it, and you find it's like very, very good. So my question is like how, because there are a lot of algorithms and a lot of papers on algorithms coming out every year, and how do you decide which ones are worth to implement?
Well, okay, I don't think there's a short answer to that to that question, but when we're deciding which ideas to implement, so you need to have a development team that can implement ideas very quickly, and you need to have various ways to provisionally test ideas. Now, we can definitely make mistakes, but probably only 1 in 10 ideas that get tried show really any promise whatsoever. But they're just very quick and very good at implementing, making initial implementations of things and looking at them. And we can do a pretty good initial test in just a few hours, because we have literally 200 machines that are constantly running comparisons of one kind or another. And they have various filters they have to go through, and I won't describe all of them. There are probably 4 or 5 steps that an idea goes through, and when it gets past the first, 3 or 4 steps, at that point you're getting pretty serious. You're thinking very carefully about the implementation and testing much more carefully.
What does the first step look like? Like from the paper to like how do you decide which paper to pick? Like what are you looking for?
Well, you're going to be a little disappointed by this. So when it comes to mixed integer programming, there haven't been very many ideas that have come out of academic research in the last few years that have had much influence on the solvers. There has, as I was in an earlier conversation today, I was describing, there's, of course, there was this big event in 1998 and had a huge effect of what was in the literature at that point. Since then, there have been some additional stuff in cutting planes, not a whole lot that wasn't known. It's been, tweaking and tuning, and some additions that have occurred. There have been some important developments in heuristics that are in the general literature, ideas based on something called rinse. Symmetry, there's important contributions from the research literature on symmetry for mixed integer programs. That's pretty much it. I don't think there's been a single idea out of the published literature that's made it into the code in the last 5 years.
Okay, we need to work harder.
Yeah.
Thanks, Cheng, for the question.
That's not true in linear programming. That's not true, by the way. There's an idea called soft symmetry, which is relatively new. It's different from the kind of symmetry that's applied in mixed integer programming. And there's as I mentioned earlier, there's a presentation by Sung Hao Gu, which he says exactly what it is. And that idea is in the open literature.
What are you thinking about using?
Chang, maybe we should
idea
continue this discussion in the next session.
Okay.
So if you don't mind, so I will maybe quickly ask the remaining 2 questions for the sake of the time. So Jiaming was asking, what's your opinion on open source in operation research? Because for instance, machine learning revolution based actually on open communities. So there's this kind of a mismatch between operation research and machine learning communities.
Yeah, there is a mismatch there. The machine learning AI communities in general, it's really very much an open source community, but we're not about to make Gurobi open source. And the comparison between the open source solvers and the best solvers like Express, CPLEX, and Gurobi it's immeasurable. The difference you can't. I mean, the differences are. You can look at benchmarks. The benchmarks tell you nothing. If you look at the public benchmarks for something like, the most commonly used open source solver is LP-Solve. You look at the benchmarks, it's totally misleading. They report some fraction by which it's slower, but it doesn't solve any of the models. So it's hitting the time limit in every case. If you increase the time limit by a factor of 10, it would be 10x slower. Pick your time limit. The solvers are truly terrible, but it is a mismatch. It's absolutely a problem that whole community thinks and so forth. They're coming around though. We're sensing a general realization that that model is not going to work across the board, open source. But that way of thinking is definitely out there, and it's an issue.
And Elias was also wondering, and that's also something that I would love to ask, any plans to make the Gurobi callbacks API more research friendly, flexible? For instance, CPLEX callbacks allow much more involved functions that can change the solver behavior. Actually, none of them would allow us to add columns during the branch and bound, not like anything to give us more freedom, if you like.
So the big major callback that we have never supported within Gurobi that CPLEX has had for years was branch variable selection. That's the big one, really the main one that was missing. And the reason for that was that when you turned that on, if you've used CPLEX, you note that you had to turn off dynamic search. I think that they have started to figure out a way around that. So I can't guarantee you that that's going to make it, but there's been some changes in the recent versions of the callbacks, and I have to admit a little ignorance. I can't answer that question. I can probably, between now and the next session, I can ping Ed Rothberg and ask him if there's been any change there. And with some luck, I might get a response.
Thank you. Yeah, we would appreciate it.
Yeah, sure.
I believe there is one last question, if you don't mind, because this has been very interesting, from Samuel Hadley, from Waterloo, actually. So if Laura can give him the permission to maybe ask the question, because I believe we didn't get it in text. So I can.
Hello?
Yes, we can hear you, Samir.
Okay. First of all, thank you for the nice talk. I'm logging in from the University of Waterloo. So we keep following your progress and the nice presentations you give. So my question is about large-scale optimization. You know that a lot of practical MIPS and LPs arising from practical applications have a structure in the coefficient matrix. And that has a huge impact on the way you solve them. So is there anything within Gurobi that uses AI to detect structure? And are you planning to maybe explore that direction in the future?
There is some of that stuff in there, yeah, now, which I'm not, I guess, at liberty to talk about, but there is some machine learning that's used currently. Not a lot, but a little bit that's used to recognize some structure. And there are some, some structural things that are used. There are independent of that. Their block structures are exploited in certain ways. This idea, when you look at the idea, if you go check out the idea of soft symmetry, you'll see that that's exploiting a sort of block kind of structure. But none of these things to this date have been really things that you can trace to a particular application area where you can say, oh, well, the models in this application area have a structure like the following. I'm not aware of anything recently that sort of had the property where there was some application area with a particular structure and we took that structure and, yeah, I might be wrong about this. I won't say what I was about to say. I might be wrong about that. But the answer about machine learning is now being used, though in a limited way, to recognize things dynamically. There've also been, there was a massive study that was done by Google, like 20 co-authors on the paper. They burned massive amounts of computing, which of course at Google is no problem, and tested every imaginable idea in mixed integer programming where you could use, where you could use machine learning to maybe decide a better branching rule choice or a better way to choose the next node that you're going to process and so forth. And that was, in spite of all that work, that was largely unsuccessful. We've looked at those results pretty carefully, and there wasn't really anything that turned into something of value in practice. But there is something that we've done in the linear programming code.
Fair enough. Thank you.
Okay. Thank you so very much. All right. Thank you so very much, everyone, for attending the seminar today and for staying until the very end and showing interest. I wish we had a couple more hours to discuss, but yeah. So with that, let's conclude this session. So Dr. Bixby, I had sent you another Zoom link.
Yes, I've got that link. And you give me,
some break if you like.
Give me about, I'm not going to take much of a break, but if you give me a couple minutes,
of course,
I've got a chat going with it. I've got a chat going with Ed Rosberg, and I'm going to nail down this callback question before I log back in. Okay.
Okay. So yeah, please feel free to join whenever you're available.
Sure, that'll be soon.
All right, see you.
Very soon.
See you there. Yeah. Perfect.